Hello everyone, welcome back to this channel. We'll be doing data preparation and EDA on and visualization on tabular data sets. So we'll begin by importing necessary libraries and we'll be using the Spotify genre classification data set and we'll be importing that, and then we'll be using the distribution of danceability music, the music that is danceable, and we'll try to distribute and see we can see that this is pretty normally distributed, and then we'll see what are the numerical feature and we'll try to plot the correlation matrix for that. And this looks like something like this. We have the columns that are danceability, energy, and key, loudness, and various features over here, and how they are correlated to each other, and we'll try to take those numerical features and we'll try to build a model out of it. And we have a genre distribution here. We have underground rap, which is listened by many people. It has a count like over 5,000. And we have the hardstyle, which is the least one. And we'll try to analyze the visualization of insights from the exploratory data analysis we did. We have a distribution of danceability. So I have this histogram that indicates the danceability values are slightly skewed towards the right. As we can see here, it is skewed towards the right. And also, we can see that with a majority of songs scoring between zero point 0.5 and zero point 0.9. So this suggests that most tracks in the data sets are relatively danceable and which allows, which aligns with beats or rhythm oriented. So what we'll try to do is we'll use energy and loudness to show a positive correlation, that is zero point 0.6, which makes sense that louder music are often perceived as more energetic. So that is how we try to find correlation between different columns, and here we'll be selecting features and we'll be dropping the irrelevant columns such as unnamed and which has type and ID and URI track, because this is unrelevant to data. What we'll be doing is they will be adding zero value to our model. So that is why we'll be removing them. And the song name column contains many missing values, and since it is also not critical, so we can either drop it or fill it missing values. So we'll be dropping that as well. And since the genre column contains categorical data, we'll try to encode it into numerical data, and the outliers like loudness, which has very low values, and tempos, which has very extremely high values, we'll try to detect that and we'll try to handle that, and we can either remove them or we can use clipping strategies. We can change it to mean values, and now we'll be trying to scale it. So for features like tempo, loudness, and duration ms, it is advisable to use scaling techniques like min-max scaling standardization. So that is what we'll be doing here, and we'll be using data encoding technique. And one hot encoder is a very nice function that can be used. And for that, we'll transform and fit the data, and we'll get the encoded genre data frame. This can be used, and will make and convert the encoded genre into data frame. Like that is what we did here using pandas library, and we'll merge the encoded genre into the clean data set which we had. So we'll get this data encoded, and the outlier detection and handling can be done. And the outliers that are present in the first and the 90th, 99th percentile of the loudness and tempo can be removed. So that is what we did here, and apply the capping. So we'll be using the feature scaling and standardization method and convert the scaled features into data frame. And that is what we did in this line. And we'll merge the scaled features back with the data set. So we'll have the final data set, which is pre-processed, and we'll now look how it looks like. So we have danceability, which has no null values, And this is somewhat how it's looking like the genre, how hardstyle, danceability, and key mode. This is all the relevant data we have. And now we'll move forward and we'll store this data set into content pre-processed CSV. So sometimes what happens when we try to build the model completely. So since the Google Colabs offer you know 12 hours of get having the resources, and when we don't sit at a stretch, we try what I've done here is I've stored the clean data set so that I don't have to rerun all the cells which were previously run, and we can start our work from here. So we'll our data pre-processing is complete, and now we'll use the pre-processed data and see all the missing values. So we have no missing values. We will be performing clustering for anomaly detection, and we'll apply k-means. So it is very easy to apply k-means, and we'll just use the already existing data set scikit-learn library for k-means, and we'll apply that, and we'll use five centroids for starting. We'll make five clusters, and then we'll copy the data, and then we'll calculate the distance of each point to its assigned cluster center. After doing that, we'll identify and remove all the anomalies for the 95th percentile distance. And then once it is removed, we'll drop the temporary columns used for clustering. So we removed about 2,116 anomalies, and we'll try to visualize the clustering result. And for that, we'll be using matplotlib. And this is what it looks like. In the first PC1, we'll be performing principal component analysis, and when we'll be seeing we have clustering visualization for PC1, and we'll have the centroids over here. So we set five clusters. So one is this cluster over here, the second one is this over here, the third one is looking like this over here, and fourth one is this cluster, and the fifth one is this cluster. So we have the different genre, and we have clustered over there. So this is the cluster center. After the PC1, we have got this as a cluster. So we'll be using AutoVIML for model building, and we'll be using that. And what we need to do is the idea here will be pretty simple. We'll import the required libraries, and and it will take care of everything on its own. It will prepare the data, it will train the data, and it will split the data on its own, and it will build the model on its own. So what we need to write is this is very low code thingy, and we will drop the target column in the beginning, which we need to target, which is the target column, that is the genre trap. And then we'll split the data, and then we'll build the model. And here we will give it the train as the train data, which is the combined training data set. And this is the test data we have. And this is the target column, that was the genre trap. Now we will start building the model. It will take some time. Uh, Use the Solov method, and it is highly recommended. And once it is done, we can see models predictive probability histogram, and it predicts this is the highest one, and we have a score of 99.5% and a balance accuracy of 98.92%, which is pretty high. And once it is done, we have a accuracy of 99.5%, which is pretty great. And we'll see what all um, it used. It used ADA boost, naive bias, decision tree, and bagging classifier. So it gave almost 100% accuracy for ADA boost, which sounds a bit for different one. We try to assemble the model's result, and we see that ADA boost has the highest one, I think. And once we're done, we'll try to get the data and save the model. And in conclusion, we can say we embark on a complete end-to-end AutoML workflow using AutoVIML. And what we covered is we data loaded the data, we did the pre-processing, we started with the pre-processed data set containing various musical features such as danceability, tempo, loudness, and genre. After ensuring that the data set was clean and structured, we split into training and testing data set, and we used AutoVIML to build the model. We utilized AutoVIML to automatically handle feature selection, hyperparameter tuning, and model training. And once that was done, we performed we performed assemble modeling. We had different ADA model and different models that were assembled. And after training, we used the train model to predict the test set that we you first split into test and training data sets. And the AutoVIML had streamlined the entire machine learning workflow by automating feature engineering and model selection, and also the hyperparameter tuning, which sometimes get pretty complicated. So its built-in assemble learning capability enhances the model's robustness and performance. I hope you learned something out of this video. This video used AutoML library called AutoVIML. This is pretty game changer when it comes to the AutoML workflows, and we have done the data preparation and exploratory data analysis and visualization of tabular data for using the AutoML library. Thank you so much for watching the video. I hope you enjoyed the video. Like and share the video. Thank you.